Hey, long time no see. Sorry for my prolonged absence from the interwebs. All right, what I have for you today, since we've decided to just talk about different topics in geometry, what I have for you today is a little food for thought regarding similarity. Similarity is amazing. There's so many cool applications for it, so many cool things you can do with it, and it all begins with, yeah, proportion. You see what I did there? Yeah. Yeah. Okay, so proportions are based on ratios, which of course you know as something like A over B. That's a ratio. It's just a relationship between two numbers. No big deal. Now, proportions come in when when one ratio is equal to a different ratio. All right, so A over B equal to C over D. Now, of course, you understand that sometimes when you're dealing with algebraic problems that it's a little challenging when you've got fractions. So sometimes you might want to get rid of the fractions, and the way to do that is by just getting rid of these denominators in the equation. Now, on this side, you'd have to multiply this fraction by b in order for those to divide b divided by b to equal 1. But you can't just multiply one side by b. Multiply the other side by b. Okay, so now you're left with a equals c over d. Excellent. Sorry, b c over d. All right, so it's already a little bit easier. Okay, now to get rid of this one, you just multiply this fraction by d. Of course, you have to do the same to this side. So over here, you've got AD, and on this side, you have BC. That is much easier to look at than something like that. Much easier to work with. Now, because you understand the math behind it, you can also see that relationship here. A times D is equal to B times C is, in the end, how this all plays out. Some people call that cross multiplying. I can't stand that. Cross multiplying is a term either for people who I would never use it. Mainly for maybe people who don't really understand this math that's going on here. But in the end, it is really useful to know that when you've got a proportion, you can just kind of change it around because you understand this math. Okay, so that's how you work with proportions mathematically. Goodbye. Now, geometric mean is a really cool sort of proportion. Because as you see, this number b repeats in both the denominator and the numerator of a different fraction. So b would be called the geometric mean of a and c. So it's cool. It's this number that relates a and c together in this specific way. How to apply this? There's actually a field called applied geometry. Not surprisingly, it's useful with useful in construction, architecture. But Jacobs in the book gives a good example about a dam, and this specifically was a setup that he had in the book. And you can read that example if you'd like to. There's an entire chapter on similarity in the book. I think it's chapter 8, chapter 9, I don't know, something like that. Okay, so what this says is that if you have a triangle here, and you've got a line that's parallel to it that goes through the triangle, intersecting both other sides, then it sets up these really cool proportions. All right, it says that that side is, or that segment is to that, ET is to TA, as EH is to HN, which is pretty cool. You can also, when you work with that a little bit, you can come up with these. These are actually a sort of a corollary to this statement. And that says that a portion of it, ET, is to the whole side, EA, as EH is to EN. So there's some really practical uses for these. Oh, of course, there's also the same as this, but using the bottom segments instead. So TA is to EA as HN is to EN. So it gives you a lot that you can work with. One specific area, and this is why I chose the similarity topic, is because we had been talking about fractals, and I had said that the main two requirements for fractals are that there's some sort of repeating pattern, and that pattern is self-similar. And I wanted to kind of explain that a little bit more, what that means. And that just means that any of the shapes, any of the repeated shapes, from the very tiniest ones to the very largest ones, they all maintain the same proportions relative to one another. So they're self-similar. All of the shapes, no matter what size, no matter what scale, are similar to the others. So similarity between shapes is, this is pretty easy to see, right? That these shapes are similar. I mean, they look like that. In your vocabulary, you'd probably already think, oh yeah, those are similar. But what that actually means, mathematically speaking, is that the sides, their sides hold equal ratios. All right, so the sides are proportional to one another. So 1 is to 2, is 2 is to 4, is 3 is to 6, and you can go on and on. You can imagine that their perimeters are also similar. Their areas are going to maintain a similar proportion. Their angles, what do you think about their angles? This is one of those other ones that's just pretty intuitive. Their angles are equal. So for this one to be similar to this one, angle C has to be equal to angle S, H to T, I to P, R to O. It doesn't need to be a square. I chose a square because it was the easiest to do. I could do any sort of crazy shape that I wanted to. You guys happen to have an amazing tool, that determines similarity. Let's see if this works here. All right, so here's one of the cool lines from the Climate March last week. You have your 2 fingers, and that's all it takes. So you have this awesome tool that maintains proportional shapes. It stays proportional. So this figure is proportional to that figure, right? So I think that that's pretty cool that you are this generation that grow up with this understanding that all it takes is, and that keeps it similar no matter what's happening. I like that. Anyway, let me just show you an example of a good fractal. And you can kind of see the self-similarity that I was talking about. You can see the small black triangles. You can see the larger orange triangles. You can see the large blue triangle. You can actually keep dividing this up. You could divide this triangle up. And you can kind of see that I took this first triangle to begin with, the large one, and then I cut each side in half. And I made this shape in the middle, which divided it into 1, 2, 3, 4 of those orange triangles. And then I took one of those orange triangles and I divided that up into 1, 2, 3, 4 smaller ones. And you could do that the same thing. You could divide this black triangle up into 4 green triangles, whatever. And you could just keep going infinitely. And you could make this square larger. You could couple this with an upside down triangle and a right side up triangle and then a right side triangle up at the top. And you could make it grow exponentially if you wanted to. That's based on Sierpinski's triangle, if you've ever heard of that. Done by another way. I was saying that you could do it to any shape. One easy way to do it to a shape is to just take a rubber band stretcher, and you could, if you were tracing one shape, whatever it is, in the middle, if you used a double rubber band, then you would make it twice as large. Okay, and another way to do that is with on a plane, on a Cartesian plane, or otherwise known as graph paper, is to take coordinates and do the same thing. You can double a set of coordinates, or triple, or quadruple, or whatever. So here is a little family. These are 2 members of the Wump family. I started with coordinates for Mug and doubled all of those coordinates. So I wound up with Zug. You want to look? You want to see Mug and Zug? Here, come on. Um,
You're talking to yourself.
I am. I'm kind of talking to myself. I do that sometimes, don't I? I think I am almost at the end. I basically just want to say that there are two other.
Look at the paper.
I see.
Why are
We
they
had talked
on the
about.
ground?
Okay, they're on the ground because I don't need them anymore. It's okay. Give me just one more minute. What we've talked about with shapes is congruence between shapes. You can also talk about similarity between shapes, like that Wump family. I'll get them back. These two guys are similar. And the way you know that they're similar is that their sides, so that side, but you could do it you could do it all sorts of ways. That side is to that side as that one is to that one. Or that ear is to the face as his ear is to his face. Any sort of, there's all sorts of different proportions that hold between these two people. Now, when you are trying to determine it for a polygon, or triangle, let's talk about triangles because that's something we've worked a lot with, congruence of triangles. There's also similarity between triangles. And one way that you can determine that triangles are similar is if two angles are the same. If two angles are the same, the two figures must be similar to one another. You can kind of picture that. What's funny to me is that if two angles are the same, the third angle, by default in a triangle, those have to be the same too. But I guess the simplest version of it is just the two angles. One angle wouldn't be enough to do it. Two angles is. As soon as you've got two angles that are the same, you know that the two triangles have to be similar. So that's like kind of the rubber band concept. That if you were to take it and just kind of stretch it out so that the sides were a little longer, then you can envision that. The other one is that side angle side also holds for similarity. Now, these are not, the angles are going to be equal. The sides aren't going to be equal to the other sides because then you'd know the triangles were congruent. But what they have to be is proportional to one another. So for side angle side similarity to hold, the sides so it has to be an angle, two sides and an included angle where the angles are equal and the sides are proportional. So that's it. So that's a brief look at similarity for you today. Have a good one. See you tomorrow.